I wonder if I have any students. Let's see. Oh, gee. Oh, yeah, I've got Ryan. Yeah, good for you, Ryan. You're 6 minutes early. Let's see. I need to adjust something here, maybe. That's supposed to say October 12th. Okay, now just a minute. It's supposed to say Monday. That's not too bad. Monday, October 12th. Yeah. Okay. Dynamics. And do I need to scoot this over a ways, maybe? Like that? Maybe. Okay, well, Ryan, good to have you this morning on a beautiful Monday morning. Did you have any questions for me?
I do not.
Okay, well, that's all right. Well, I guess I could write down our topics. Let's see, we're going to study conservation of linear momentum. Gosh, that's going to take up too much space. But that's what we're going to study, so I guess I should write it. Tell you what, I could abbreviate. Conservation of momentum and the other topic is coefficient of restitution. There we go. Now we got our topic up there. Well, let's see if anybody. Oh, Nicholas showed up. Good going, Nicholas. And Ashley. We've got Ashley, Nicholas, and Ryan so far. And I need to write down your homework, I suppose. Let's find that. According to this, we're having a test. It'll be available on Wednesday. It's a take-home test. Of course, you don't need to take it home because you are home, right? Okay, well, let's see. Your test is available Wednesday the 14th. You know what? Today's the 12th. It's Monday. So, and it's due on Friday, the 17th. So you have a test. Now, what about homework? I don't know. Let me dig around here and see. Today's the 14th. Yeah, there's some homework. Today's the 14th, right? Yeah. And it looks like, no, today's the 12th. Today's the 12th. And your homework number 16 is problem 15-7 on page 248. And it's due, this says it's due the 15th. Well, that's tomorrow. Now, just a minute here. No. No, that's not tomorrow. It's due the 15th. I'm getting mixed up here. Oh, you don't get this test till Wednesday, and then it's due Friday. But you get this test today. It's available today, and it's due Thursday, right? Thursday the 15th. Yeah, I think that's right. Okay, well, we've caught up on all of that. Or have we? Or have we? Well, I think we have. Okay. Now, are there any questions?
Is the test due Friday the 16th or Saturday the 17th?
Let's see. If it's available Wednesday, the 14th, it's due. It's due Saturday. I'm wrong. There's a thank you point. Now, who was that?
That was Stuart.
Stuart, it's due Saturday the 17th, isn't it? Okay, thank you, Stuart. I think we're all ready to go. Any other comments or questions? All right, well, let's get rocking and rolling here. Oh, we got a good crowd. Look, we got Mark, Jesus, Braxton, Ashley, Tyler, Taylor, Stuart, and somebody, hey, William, and William's here. Got a great class. All right. Now, the topic today is conservation of momentum. So let's do that. Now we had the impulse momentum equation. Let's review that. The impulse momentum equation. I know I told you guys about this. It goes like this. This thing here is called impulse. These are called momenta, plural of momentum. And here you're subtracting the initial from the final, and that's your impulse momentum equation. And I think we worked some problems on that. Maybe we should do another one real quick here on that. Wonder what would be a good one to work here. The book has all these complicated ones. I wonder if we could just do a simple one. Let's just do a simple example, okay? They have to make it so complicated. Well, I'm going to erase all this if you guys are happy. It's all in your syllabus or in your Blackboard. You can look all that stuff up. So look it up. But here, let's do a simple example of this impulse momentum business. Suppose you had here, body A, 2 kilogram body A, put it on rollers, so let's don't have any friction. Let's keep this as simple as we can. And somebody has a rope here attached to it, and they're going to put a force on it there. So we'll put that in red. And we'll just make up something. Suppose they have 3 newtons of force there. Now, you know there's going to be a normal and a weight, but see, they cancel. So we don't really care about them. They cancel. And let's apply this force for, I don't know, 5 seconds maybe. For 5 seconds, we're going to apply that force. Now we're going to put this in here. Well, there's just that one force, so you'd integrate from 0 to 5 seconds, and you have 3 newtons times your delta t. And this is, start from rest. So the final will be the mass times your velocity minus 0, because we'll just assume it started from rest. And we can solve that, and we can find out its velocity, couldn't we? We don't need to integrate that. It's just a constant 3 newtons, so pull it out, multiply it by 3 seconds, and what you'll have is, 5 seconds. But what you'll have is 3, man, make some room here. What you'll have is 3 newtons times 5 seconds is equal to 2 kilograms times VA. Okay, so you get 15. I can do that in my head. I'm getting 7.5. I'm getting the velocity of A is going to be 7.5 meters per second at the end of 5 seconds. See, it's going to speed up. It starts off at 0 and it goes faster and faster. And we just use the impulse and momentum equation. Now, you know, we could have done that problem with Newton's second law. Just for fun, we'll do that. See, Newton's second law says in this case, you just have 3 newtons, 2 kilograms, and you can solve for the acceleration, which is, I can do that in my head. It's time to show off a little bit. I'm getting acceleration of 1.5 meters a second squared. Now, if you want the velocity, we have an equation that goes like this. This is 0, it starts at rest. So what's 1.5 meters a second squared times 5 seconds. Well, boy, Jude, it's 7.5 meters a second. You get the same answer using Newton's second law, don't you? Any questions on that? That's pretty simple, I think. Okay, now we're going to talk about collisions, though. We're going to talk about collisions. And in a collision, you have conservation of momentum if you can neglect any other forces. If the only forces you need to worry about are the collision forces. Let's take our, what was it, 3 kilograms? I forgot. We'll take our 3 kilogram body and maybe a 2 kilogram body. And we could have a kind of a head-on collision. Well, why don't we have him going slowly this way and him going fast this way? We'll just make some stuff up. Suppose this is going, what did we have before? 7.5 meters a second. And suppose this one's going 2 meters a second. Well, they're going to collide, aren't they? Now what's going to happen is there's going to be a collision. A is going to come over here, and A is, I think I made A too big. Just a minute here. A is going to collide with B. Yeah. And see, they'll just touch at the beginning of the collision. There's B. These could have rollers on them so that we don't need to worry about friction, okay? It's supposed to be a smooth, that was supposed to be smooth. See, this is the beginning of the collision, and then what happens is the collision is really very fast, maybe, I don't know, 1/100th of a second or something. When two blocks hit each other, they just go click, bam, and that's over. It's very, very fast. But see, A puts a force on B. A puts a force on B. But did you know that B puts an equal and opposite force on A? Newton's third law says so. Newton's third law says, for every action, there's an equal and opposite reaction. You might try it here, a little home experiment. Clap your hands. You got 2 hands. We're going to clap them. Here we go. Ready, get set. Ow, that hurt. That hand kind of stings a little bit because this hand hit it. But you know what? This hand kind of stings a little bit because this hand hit it. And they sting about the same amount because the force on this hand from this hand is the same force of this hand on that hand. Newton's third law says, for every action, there's an equal and opposite reaction. So whatever the force of A on B is, the force of B is equal to the force that B has on A is equal to the force that A has on B. Kind of makes sense. Now, if you want to look at the total impulse for both bodies, if you're looking at both bodies, the equation goes like this. if you're dealing with both bodies, this term will be zero because, see, the force, the impulse on B, this is called impulse. The impulse on B is going to be, it's going to be that force times dt, going to the right. See, these are vectors. That's going to the right. But the impulse on A is going to the left, so you'd have to subtract. But see, here's the thing. They have the same force, and they share the same time. Actually, this is a plus, and this is a vector. These are vectors. So it amounts to subtracting. Can you see that the total impulse will be, zero? And therefore, what you have here is the sum of all the final momenta minus the sum of all the initial momenta. You can do a little algebra there. Let me do that algebra. And here's what you'll get. Can you get from here to here? Can you make it? Well, they have a fancy name for that. The sum of all the final momenta is equal to the sum of all the initial momenta. They call it the conservation of momentum. Actually, it's the conservation of linear momentum. There's another kind of momentum called angular momentum, and we'll talk about that later. But there's also a law of conservation of angular momentum. But right now we're doing linear momentum. So we just showed you the equation there. All right. Any questions or comments from anybody? Okay, well, we're having a little theory session right now on conservation of momentum, and I need to explain the coefficient of restitution. But let me talk to you about collisions for a minute. If I can erase all this, if you're happy. Okay. All right, I'm going to erase all this. Well, actually, I could leave that up there and we could use it as an example. There are three kinds of collisions. There are three kinds of collisions. I wonder if anybody knows what they are. Let me just go and let me ask somebody. It's okay if you don't know, because that's what you're here for. You're here to learn, right? Shane, unmute and say hello, Shane.
Hey, how you doing?
Hey, I'm doing great. Shane, do you know any of the three kinds of collisions?
I know one's elastic.
Yeah, good going, Shane. Elastic. Good going. Do you know what the meaning is? What does that mean if it's an elastic collision, Shane? Do you have any idea?
It stretches.
Yeah, you can say that. Yeah, it stretches. Yeah, that's right. You don't know the other two, though, right?
Inelastic.
Yeah, good going. Inelastic. But Shane, you don't know the other one.
No, I don't know the third one.
Yeah, that's fine. Now, actually, probably a better name would be perfectly elastic. Perfectly elastic. And then there's perfectly inelastic. But Shane's heard about this. There's perfectly inelastic. Now see, those are the two extremes. And you've probably studied those already. I bet you've had those maybe in Physics 1 or in high school or something. But there's an in-between kind that we're really going to focus on in here today. And they have a name for it. They call it elastic. Just a minute now. I don't want to tell you the wrong thing here. Let me see what the book calls it. Just a second. Let me dig the book out here. This is chapter 15 that we're studying. And I forget what they call it, but I'm going to look it up here. Maybe you can find it and tell me before I can find it. Okay, I'm digging through the chapter 15 here, trying to find this other kind of collision. But what it is, it's in between, see? It's partly elastic and partly inelastic. But what did they call it? I don't know. I don't know if they tell us here, but let me, just a minute. I'm not quite through trying to find it here. Okay, well, we're just going to call it, until I can think of a better word, we'll call it actual, real world, maybe. This is the kind of collisions 99% that happen. I don't know if you've ever been in a collision. I have. I've been rear-ended twice, I think. Once was with my Camry. I love that Camry. And once was with my Taurus. I love that Taurus too, but I guess I need to speed up so people won't rear-end me. I love that Taurus. You know, the nice thing about that Taurus is, according to statistics, it's the least stolen of all the vehicles. Nobody steals Tauruses. That's what I liked about it. I didn't need to worry about anybody stealing it. Now why they would not want to steal my Taurus, I don't know, because I loved it. But see, this is the real world kind of collisions. Now, if you want to know the definition, an elastic collision, the kinetic energy is conserved. So the total initial kinetic energy, that little I stands for initial, is equal to the final kinetic energy in a perfectly elastic collision. Now, in a real world collision, the way it works is the total final kinetic energy is less than the initial kinetic energy. Because see, what happens is you lose some energy in heating up. When vehicles collide, if you go over there right after the collision and touch the bumpers, they're hot. They get hot. Well, it's kind of like if you take a hammer and you beat on an anvil for about half an hour, that hammer gets hot, and the anvil will warm up too. See, there's some energy in heating things up. So In an actual collision, the final kinetic energy is less than the initial kinetic energy. Now, what about an inelastic collision? Well, this is true also in an inelastic collision, but what's different about it is the bodies fuse together and have the same velocity. The velocity of A and the velocity B, the final velocity. Let's maybe put an F on that. The final velocities are the same because they stick together. Here, let's do an example. Suppose you had this deal here. This one's sitting here at rest. And here comes this body A, and it smacks into it. Let's do the perfectly inelastic collision, and we'll show you what happens. And then we'll do an elastic collision. Here we go. Okay. If they stick together, I don't know how you could do that. Maybe put a drop of super glue right there, and when they hit, they just stick together. Okay. But in any case, in all three collisions, momentum is conserved. So the initial momenta has got to equal the final momentum. Now the initial momentum is and the final momentum is do you see when they stick together, the masses add up and you have 5 kilograms and they're both going at the same speed, and you can solve for that speed. Go ahead and do that. Find the speed if they stick together. I can't do that in my head. I got an answer. Let me go to one of my students here. How about my friend Tyler? Tyler, unmute and say hi.
Hello.
Hello. Tyler, did you get this final velocity if they stick together?
I got 4.5 meters a
That's
second.
what I got. I got 4.5 meters a second. And see that they've stuck together. This thing was going 7.5, and this was at rest. Then they have a collision, and they stick together, and now they're going 4.5. Now you lost some kinetic energy. Let's do that. Let's get the kinetic energy. That'd be fun. Now the initial kinetic energy is, well, it would be 1/2 the mass times 7.5 squared. And the final kinetic energy is 1/2 5 kilograms times 4.5 meters per second squared. Okay, go ahead and get that, and I'll call on another wonderful student. Go ahead and find the initial and final kinetic energies. Let me go to one of my excellent students here. William, unmute and say hello, William, please. Earth calling William. Earth calling William, come in, William. Uh-oh, coffee break. Tyler. I don't think I picked on you yet, have I, Tyler? Tyler, unmute and say hello. Earth calling Tyler, come in, Tyler. Uh-oh, coffee break. Stuart is not, he won't let me down. Stuart won't let me down. Stuart, what'd you get for the initial and the final kinetic energy, Stuart?
For the initial, I got 84.375, and for the final, I got 50.625.
That's what I got. Now, what are the units on that, Stuart? We need units.
Is it joules?
Yeah, good going, joules. Hey, we lost some kinetic energy, didn't we? Hey, Stuart, where did that loss, where did it go? It went someplace. Energy just doesn't go poof and disappear. Where'd it go? Stuart's thinking. So you had 84 joules before the collision. After the collision, you got 50 something joules. Stuart, we're missing about 30, close to 30 joules. Where'd it go, Stuart?
I'm not sure.
Yeah, that's okay. Remember, after a collision, right after the collision, go put your hand on the bumpers. What do you feel on that bumper, Stuart? On that bumper, what do you feel?
Heat.
Yeah, it's hot. It's hotter, isn't it? Yeah, it's hotter. And so where'd the energy go? Come on, you just said it. Say it again.
I just wasn't sure how to word it. It went into the heat.
Yeah, that's where it went. It went in heating up I guess both blocks are going to be a little warmer after that. Did you know, I've never been to Niagara Falls, but if you take a thermometer and measure the temperature at the top of the falls, and then take your thermometer and measure the temperature at the bottom of the falls, did you know it's a little bit warmer at the bottom? How about that? It's warmer at the bottom of the falls. See, it'll be warmer after the collision. Well, that's interesting. Now that was the third kind of collision, the totally, how did I put it? Did I say perfectly inelastic? Let's do an elastic collision. And then we can do one in between. That'd be fun. Here we go. I need to erase all this if you understand it. If you understand it. Now, what you got to know is this equation here is still good no matter what kind of collision it is. This equation is called the conservation of momentum. And I don't care what kind of collision it is, the momentum is still conserved. And I explained why. It has to do with the forces are equal and opposite, and the time of collision is the same for both bodies. So the impulses on the bodies are equal. They're opposite, but they're equal. Impulse is a vector. They add up to 0, and so you get no change in momentum, total momentum. But now let's do an elastic collision. Now there's another equation that I want to talk about today. It's called the coefficient of restitution equation. It goes like this. Put finals on that. Put initials on this. And I'll show you where this equation comes from here in a little bit. But this is called the coefficient of restitution equation. That's the name of it. Yep, there it is. You're looking at it. That's the coefficient of restitution equation. And I'm going to explain where it comes from here. Well, or you could read it in your book. It's on page 267, but I'll discuss it with you. Now, here's how it works. If you have a perfectly elastic collision, here, let me write this for you. Perfectly elastic collision, E equals 1. If you have a real world collision, like when my Taurus got rear-ended, you'll find that the coefficient, they call this the coefficient of restitution. You'll find it's bigger than 0, but it's less than 1. And then the last kind that we just did, what do we get for our answer? I forgot. What did we get for our answer on that last one? Was it 4.5? Is that what it was?
Yeah.
It was 4.5. See, and this is a perfectly if you have a perfectly inelastic collision where they stick together. If you have a perfectly inelastic collision, the coefficient of restitution is 0. So you have 0 for this, 1 for that, and all the others are in between. Well, let's do one of those. Suppose this was no, we did one of those. We checked that off and we got an answer. And I forgot, but was it 4.5? Was it 4.5 meters a second? Is that right? Somebody
Yes.
say, uh-huh. I should take notes on this. I need to take notes on
Yeah.
my own lecture.
Yeah, that was right.
Good deal. Okay, now what we're going to do is we're going to do one of these. We're going to do a perfectly elastic. Well, see, if that's 1, okay, if that's 1, then, what did I just do? Did I just break something? Oh, gee. I better be careful here. Everything could come tumbling down. Let's see. We've got the BF final. Well, I don't know what the BF initial, BA final is. I don't know what they are, but I do know what the VA initial is. It's 7.5. We're going to have to do some algebra to get this one. It's 7.5, but the BI initial is 0. Remember, it was at rest. So we have a lovely equation there. I need the room to work. I need this room to work. We got to do some algebra now. Now, I shouldn't have erased my conservation of momentum equation, but I tell you how it went. it went like this. 3 kilograms times 7.5, that's all you got initially, is going to equal to the 3 kilograms VA final plus the 2 kilograms VB final. All right, well, we got 2 equations and 2 unknowns, and we're just going to do some algebra now. Let me rewrite this one here. Multiply by 7.5. And write this as BF final minus 1 VA final plus 1 VB final. There we go. Well, all I did was rewrote this equation here down here, and now I'm going to solve it. Well, what's the best way to solve that, I wonder? I don't know. Maybe, tell you what, multiply everything here by 3. Let's do that. That'll be good. If you multiply this by 3, you'll get 3 kilograms times 7.5 meters a second. This you'll get minus 3 VAF. And this you'll get 3 VBF. What I did was I took this equation and multiplied it by 3. I don't need it anymore. Now what I'm going to do is add these equations together. And the VAF cancels, and you're left with 5 VB final. That turns out to be a 0. And this will be, well, I can do that. It's 6 times 7.5. It's 45. And so VB final is, what's 5 into 45? It's 9, isn't it? According to this thing, it takes off going 9 meters a second. Well, what's VA final? So that's the final. Let's get the VA final. Now, how would you do that? Well, you'd have to plug it in one of these. I think it's 1.5. Let's check it. This is called checking your work. These are my answers. Now, if I plug them in here, let's see, does that work? Let me try it. Let's see, 3 times 1.5 negative plus 3 times 9. I get 22.5. What's 3 times 7.5? Well, boy, Joe, it's 22.5. You know what? I think I've got the right answers. Okay. Well, let's plug this in and get the kinetic energies. Do we have any questions yet? Okay. I'm going to talk about this equation here in a minute, but we think we have the answers in a perfectly elastic collision. I need some room now. Now we did a perfectly inelastic collision. And we found that the final velocity of A was equal to the final velocity of B, which was equal to 4.5. Now, on the perfectly elastic collision, we have the final velocity of A is 1.5, and the final velocity of B is 9. Okay, let's get our initial kinetic energy. The initial kinetic energy will be 1/2 3 kilograms times 1.5 meters squared plus 1/2 2 kilograms times 9 meters per second squared. Okay, get that. Let's see what the initial kinetic energy is. And we'll also do the final kinetic energy. The final kinetic energy will be 1/2. No, wait a minute. That was the final kinetic energy, wasn't it? Yeah. Sorry. That's the final kinetic energy. The initial kinetic energy is 1/2 3 kilograms times 7.5 meters per second squared plus 1/2 2 kilograms times 2 meters per second squared. Now we're going to find the final kinetic and the initial kinetic energies. Go ahead. I'll shut up. Find the final and initial kinetic energies after the collision. Well, I got the final kinetic energy. I wonder if that's what you got. If that's what you got, say uh-huh.
Yeah.
Yeah, there's somebody. Let's see if I can get this right. Houston, we have a problem. They're supposed to be the same. So maybe I made a mistake. Okay, I made a mistake because these have got to be the same. They've got to be the same, so I must have made a mistake.
I think what
Okay.
happened was when you were finding the elastic, you set the initial velocity for B as 0. I think it should be 2 meters per second.
Yes. Yes. The initial velocity of B should be 2. Honkin', thank you. Who was that?
That was Stewart.
Stuart. I appreciate that. In other words, I think we got these answers wrong. Let me do it over again. Man, I really appreciate that. Let me do it over again. You guys have to stay awake and help me here. So these are going to be wrong. Now that one there, I think everybody agreed on that one. But to do this, you have to take the coefficient of restitution. And let's see if I can get this right. And see, this should be 7.5 minus 2. And I think Stuart told me I had a 0 there. And so this equation is going to be 5.5 equals VBF minus VAF. And then the other equation, we had, let's see, what's 3 times 7.5? This is your total momentum. Just no, that's not, because you have to add 2 times 2. You have to add 4 to it. This should be the initial total momentum. Here, let me write it out. We're adding up the total momentum, the initial. It should be 3 times 7.5 plus 2 times 2. Did I get that right? 3 times 7.5 plus 4. Still not right. Okay, 3 times 7.5. That's your mass. That's your velocity. Mass, velocity. That's your initial momentum. And what you get is that's not right. What you'll get is 26.5. They're actually kilogram meters per second. That's your initial. Now the final is going to be 3 kilograms times VA final plus 2 kilograms times VB final. So we have 2 equations and 2 unknowns now. This is your initial momentum. Okay. This is your final momentum. But we have 2 equations and 2 unknowns. So we can solve it. And this time I'm going to get correct answers. And this thing, it's going to work. Okay. Tell you what, multiply this equation by 3. 5.5 times 3 is 16.5 equals a negative 3 VAF plus 3 VBF. I multiplied this equation by 3, and so I don't need it anymore. And then when I add them, I'll get 5 VBF. This will be 0. And this will be 43. So VBF is, it's not 9, it's 8.6. I was wrong before, but thanks to Stuart, he helped me out here. And now we can get a VAF. You can get it from any of these equations. All 3 of them will work. And what you'll have is, I think it's 3.1. But we're going to check it and plug that in here and see if it works. Here we go. I'm going to check it. Yeah, it checks out. Okay, well, we finally, thanks to Stuart, we finally have the final velocities. Here, I'll draw it for you. See, after the collision, A slows down. A is only going 3.1 meters a second, but B takes off. It's going 8.6 meters a second. You know what? That's what happened to me in my Taurus. Or what was it? No, it was a different car. A pickup truck hit me. It was my Camry. It was my Toyota Camry. Pickup truck hit me. I wasn't going very fast, but after he hit me, I was going fast. I really took off. This pickup truck hit me, and man, I took off. Well, see, this guy was only going 2 meters a second. Now he's going 8.6 meters per second. It's like me in that pickup truck. See, it's heavier and bigger, and it's going faster, and when it hits me, I just took off. Okay, now we're going to get the kinetic energy. Okay, well, let's see. We need the initial kinetic energy. Do we have room here? I think so. Now this time it's going to work. The initial kinetic energy is 1/2 3 times 7.5 squared plus 1/2 times 3 times 7.5 squared plus 1/2 times 2 times 2 squared. Okay, let's get the initial kinetic energy. Here goes. Well, I'm getting 88.375. You know what? That's what I got the last time. That hasn't changed. The initial kinetic energy is the same as it was before. But now we're going to get the final kinetic energy, and it's going to be equal to that. It's going to be 1/2 times the 3 times the 3.1 squared plus the 1/2 times the 2 times the 8.6 squared. Okay, plug that in your calculators. Let's see what happens. Boy, Jove, it's 88.375 joules. It's the same because we had a perfectly elastic collision. But see, the real collisions in the real world, they're really not perfectly elastic. My collision with my Toyota Camry was not perfectly elastic because the rear end was all smashed up. And to do that, the coefficient of restitution will be somewhere between 0 and 1. Let's talk about this coefficient of restitution equation. We got 32 minutes. Let's see what we can do. Do we have any questions on anything? Okay, well, let me start all over and talk to you about this equation. And you'll discover that kinetic energy is not conserved in a inelastic collision of any kind, whether it's perfectly inelastic or only partially inelastic. But let me draw you a graph here of force during a collision. Force versus time. Remember, we had two bodies. We had a body A and we had a body B. And I think B was going slower. Well, at the moment the collision starts, there is no force. Just right before the collision starts, but the force builds up very rapidly. Now, if you have a perfectly elastic collision, it goes up here. It's a nice, beautiful thing like that. This could be the force on body B. See, we're plotting force versus time. Now, this time is very small. It might be 0.01 seconds, okay? These collisions happen fast. Now, down here, what we have is the force on body B, and it's like that. It's a mirror image. Maybe down a little further, but not much. There we go. It's a mirror image. This is the force. No, this is the force on body A, and see, it's negative. Remember, when they collide, the force on A is going that way, and the force on B is going that way, but they're equal and opposite. And this is what you'd have with an elastic collision. Perfectly elastic. And we did that. And we found the answers. And we found that the kinetic energies were conserved. But in the real world, you don't get this beautiful, perfect shape. Here's what you'll get. It still happens fast. It might be 1/100th of a second or even less. But it starts off and it builds up. It builds up. And then it drops. Then it does this. This is called the restitution. This right here is called the deformation. Trying to draw this so that you'll understand. Call this D for deformation. Call this R for restitution. Call this R for restitution. The coefficient of restitution is, it's the impulse, it's the impulse of restitution divided by, I don't know if you guys can hear that chainsaw, but my neighbor has got a chainsaw and it's bugging me. Divided by the impulse of deformation. I did that. Yeah, no, I think I did that right. The impulse of restitution is smaller. Now, in an elastic collision, these would be equal because you get this beautiful shape. Now, that's the force on B. Now, the force on A goes like this. There we go. It's a mirror image. It's a mirror image. This is the force of deformation. And this is the force of restitution. Now, the area of this is the impulse of restitution. Here, I'll color it. You see this blue area here? They're making so much racket out there that it's bothering me. That area is, that's what this is. That's what this is. You all know the area under a graph is the integral. And see, this is always bigger than the restitution area. It's smaller in a real collision. They're equal in an elastic collision. See, this is the force on A. It's negative. It's going the other way. this is a real collision. Okay. Now let's label these times. Why don't we call this T0? We'll call this time right here T1. And we'll call this, when the collision is finally over, T2. So see, this restitution goes from T1 to T2. Can you see that? The restitution goes from T1 to T2, but the deformation goes from T0 to T1. Okay, and let's do the coefficient of restitution for body A, or I mean for body B. We're going to do body B. It's going to the right. Okay, well, we have an equation that goes like this. And we're talking about body B, and it would be body B at the time 2 minus body B at the time 1. That's just the impulse momentum equation. Now in the denominator, what we have is the velocity of B at time 1 minus the velocity of B at time 0. You all know the impulse momentum equation. The impulse is equal to the change in momentum for those different times. Now we're going to do a little algebra here. Since I got MBs everywhere, I could just write this as VB2 minus VB1. And I could write this as VB1 minus VB0. That was for body B. Now let's do the same thing for body A. Here goes. For body A, it's the impulse of restitution. They call this the impulse. And that goes from T1 to T2. And here's the impulse of deformation. We're talking about body A now. Now, to be honest about this is negative because it's going the other way, but so is this. This is negative, and it's going from T1 to T2. But you know, those negatives cancel out. We could get rid of them. We don't need those stinking negatives. Just forget it. And so this is equal to, we're talking about body A, velocity at 2 for A, minus mass of A, velocity of A at 1, divided by the mass of A, we're talking about body A, velocity of A at 2, minus mass of A, velocity of A at 1. So we've got two equations. Now these are both equal. They have the same coefficient of restitution. You can see that. You can see the areas are the same, and so the ratio of the areas will be the same. And so we could set this equal to that. Here, get rid of all those MAs. We don't need those stinking MAs. VA2 minus VA1. We're almost done. If you've stayed awake through this whole thing, you're a better man or woman than I am. Good going. And we're almost through. We got one more step and we're going to be through. We're going to have our coefficient of restitution equation, if you followed all that, which is a mighty big if. I'm going to show you a little algebra trick that you might not be familiar with. If you had something like 12/16, is that equal to 3/4? I think it is. It's equal to 3/4, isn't it? Somebody say, if that's right.
Yeah. Yep.
Yeah, that's right. Well, here's something maybe you didn't know. Whenever you have two equal fractions like that, did you know you can take the numerators and subtract them and subtract the denominators? And of course, that would give you what? 9 twelfths? No. Yeah, 9 twelfths. Well, you know what? 9 twelfths is equal to 3/4, isn't it? Isn't that clever? Did they teach you that in 5th grade or not? Probably not. But it's a fact. And so what we're going to do is we're going to take these numerators and we're going to subtract these numerators. And we're going to divide, we're going to take this denominator and we're going to subtract that denominator. And here's what we're going to get, if you followed that. Any questions on that? All right. Well, here's our final lovely equation for coefficient of restitution. It's going to be this numerator minus this numerator. Let me write it out. VB2 minus VB1 minus VA2 minus VA1. See, what I did was I subtracted numerators. Now we're going to take this denominator, VB1 minus VB0, and we're going to subtract this denominator, which is VA. And wait a minute. Yeah, that's right. VA2 minus VA1. Wait a minute now. I got a bad feeling about dang. I'm gonna knock everything down here. I got a bad feeling about this. Just a minute. Okay. No, I think that's right. Now here's the thing. You know what? You see this VB1 and this VA1? They're the same. I'm doing something wrong. Just a minute. Okay, just one tiny minute here.
I think the denominator on your EA equation is, it should be VA1 minus VA0.
This denominator here?
Yeah, for the A equation.
Okay, now I'm subtracting that. Now I'm taking the VB1 minus VB0, subtracting VA2 minus VA1. That's not right?
Should that be VA1 minus VA0 on the bottom?
Okay, now just a second. We're going from 1 to 2, so this would be 2s and that should be 1s. Going from 1 to 2s, that should be 2s and that should be 1s, right?
So you go from 1 to 2 on both the numerator and denominator for the A?
Say that again, please.
On your EA equation,
Yeah.
you go from 1 to 2 on both the R and D?
Okay, now just a minute. I want to go restitution, so that should go from 1 to 2.
Right.
So there's
Yeah,
final
right.
minus initial. I think I did that right.
But on the bottom, you're also going from 1 to 2. Do you not go from 0 to 1?
Okay, now just a minute. For the deformation, I want to go from, this is wrong. This should be VA1 minus VA0, huh? See, the deformation goes from 0 to 1. Deformation goes from T0 to T1. See, the deformation goes from 0 to 1. So that should be TA1 minus TA0. Okay, that's better. So this should be TA1 minus TA0. Did I get this right? I think I did. Okay, now let me get this right. I subtracted the numerators. I think they're okay. Now the denominators, I got VB1, VB0 minus Okay, now here's where I goofed up. And there's another couple of thank you points for you guys. I really appreciate you guys staying awake on this. Now here's the thing. You see that VB1 and that VA1? They're equal. This is the velocity of B in the middle of the collision. See, in the middle of the collision, they're both going the same velocity. That's when they have the maximum deformation and they're getting ready to bounce. They've compressed, they've smashed, and they're both going the same speed, and then they start spreading apart. Let me circle that. I've got a red pen here. Do you see that VB1 and the VA1? They are equal. A and B are going the same speed at that time one, and that's a minus, and there's two minuses, that makes a plus. So this disappears. Now down here, this VB1 and the VA1, they are the same speed. Right in the maximum compression there, you've had this head-on collision and your radiator is being shoved back, but both vehicles are going the same speed at that maximum of the collision. And so here's what you get for your answer. You'll get VB2. Now wait a minute. That says plus VA2. That can't be right. And this will be VB1. This will be VA0 minus VB0. But this is going to be VB2 minus VA2. Yeah, that's right. And then this is VA0 minus VB0. Yeah, that's right. I think that's correct. And I think you'll find that equation. Look on page 267. Look on page 267. Look, they have a VB2 minus a VA2 divided by a VA. They use a different symbol. They're one. They call this one here to start with. I call it 0. But what these are those are initial velocities. Hey, we've got it. We've got our coefficient of restitution equation by some miracle and your help. We have got it. Now, if we had some time, I would love to do an example. I would love to do an example. If you didn't understand any of this jazz, let me write this out for you so that it'll be useful to you. In a real world collision, you can use this equation here. It's your final velocity of body B minus the final velocity of body A. That's what it says. Divided by the initial velocity of body A. Why don't we put an I there maybe? Minus the initial velocity of body B. That might make more sense to you. These have a name. What that really is the velocity of B. It's the final velocity of B relative to A. It's the final relative velocity. And you know what this is? This is the initial relative velocity of A relative to B. It's the initial relative velocity. Oh, gee, I have 2 minutes left. Now, let's do our example. Do you remember what this was? Was this 3 kilograms and this was 5 meters a second? Does anybody remember? And this was that 2 kilograms and 1 meter a second? Not that it matters. But suppose that's what you had. Suppose you had 3 kilograms at 5 meters a second, 2 kilograms at 1 meter a second, and they have a collision, and we'll just make up something. Suppose the coefficient of restitution is a half, 0.5. Well, then the velocity of B minus the velocity of A. Now these are the final velocities. You can put an F there if you want. And this is the velocity of A, which is 5, minus the velocity of B, which is 1. And there's your equation. That's your coefficient of restitution equation. But that's not enough. You've got to have your conservation of momentum equation. Now, it would go like this. You know how that goes. Conservation of momentum, you would have 3 times 5 plus 2 times 1 equals 3 times plus 2 times. There's your conservation of momentum equation. Here's your coefficient of restitution equation. Look, there's 2 unknowns. This could be solved. I wish we had more time, but anyway, you've been exposed to the 3 kinds of collisions. And this one's new to most of you, I'm sure. The real world collisions is new to you. I'm sure you've had elastic collisions and totally inelastic collisions. But you need this equation, this coefficient of restitution equation. There it is. There it is. If you didn't follow my discussion, you could read the book. They do it in the book. It's sad, but our time has come to an end. And do your homework and study for your exam. I guess you get that on Wednesday, and it's due Saturday, I think we said. Okay, any last comments? Going once. Going twice. Okay, bye-bye,
Have a good day.
students. You too. Bye-bye.
Bye.
Bye.